Hi guys, it's Mrs. Seitz, and today you are going to be learning about what scientific notation is. We're going to be both reading it and writing in it. Scientific notation is basically a way for you to write really, really, really big numbers or really, really, really small numbers. So, for example, if you were to take your calculator and just type in any number, like say 3, and type in a ton of zeros behind it, and just keep pushing 0 for as long as you wanted to, and then hit enter, you might get this weird notation. So a 3, a 10, and then some exponent. What's happening is your calculator can only hold so many spaces before it kind of runs out. And what happens is with really, really big numbers, this is the way your calculator can use to represent this. Some calculators might, instead of having a 10 here, might use a E instead. And this is a way for calculators to represent big numbers or really, really small, tiny decimals. So instead of having a positive exponent, it might have a negative exponent here instead. And we're going to learn how you can actually represent these today. So this is called, again, scientific notation. Scientific notation is a number is written in scientific notation when it is represented as the product of a factor and a power of 10. The factor must be at least 1 and less than 10. So again, the first part always has to be at least 1 but less than 10 and some power of 10. If you have a negative exponent, we're dealing with a tiny decimal. If we're dealing with a positive exponent, we're dealing with a larger number. So for the first part, we're just going to even see if the number is properly written in scientific notation. So again, if I look at the first part, I'm looking to see 2.5. Is this a number between 1 and 10? Yes, it is. The next thing I'm looking at, do I have times 10 to some power? Yes, I do. So the correct answer for this is yes, this is in scientific notation. For question number 2, again, the first thing I look at is the factor. Is 0.5 a number in between 1 and 10? And the answer to that is no. And you would write factor is less than 1. So again, the factor needs to be a number between 1 and 10 for it to be properly written in scientific notation. We are going to practice writing that now. So when writing a number in scientific notation to what we call standard form is writing the really, really large number or the really, really tiny decimal. The absolute value or the absolute, the value of the exponent tells you how many places to move the decimal point. So if the exponent is negative, we are going to be moving the decimal point to the left. If the exponent is positive, we're going to be moving that many places to the right. All right, so let's take a look at our first problem. We have 6 times 10 to the 7th. So I'm going to write down my factor of 6. If you're wondering where the decimal point is, the decimal point is actually, remember, behind or to the right of 6. I'm going to be then looking at my power of 7 that's on the 10. That's telling me how many places to the right I'm going to be moving my decimal point because my exponent is positive. I'm dealing with a large number. So I'm going to count 1, 2, 3, 4, 5, 6, 7 places. And then I'm going to just kind of fill those bumps in right now with zeros. Okay, now to make this nice, this is a 6 with 1, 2, 3, 4, 5, 6, 7 zeros. And you should put some commas in between there so it helps your teacher out. Okay, so the proper way to say that would be 60 million. Okay, let's take a look at question number 2. For question number 2, it's 9.9 times 10 to the negative fifth. So again, the negative 5 is telling me how many places I'm moving my decimal point to the left because I'm going to be dealing with a tiny number or a tiny decimal. So I'm going to write 9.9. And again, I'm going to count 1, 2, 3, 4, 5 places. And I'm going to fill in with zeros. So my answer for question number 2, and I'm going to put the decimal point right here, would be 1, 2, 3, 4 zeros, followed by 9, 9. And again, we're going to move the decimal point into the front because we're dealing with a tiny decimal. Okay, I'm going to erase this just for space purposes. Okay, let's take a look at question number 3. So I have 1.285 times 10 to the fourth. I'm moving my decimal point this time to the right because I have a positive exponent. I'm dealing with a large number. So I'm counting 1, 2, 3, 4. I'm going to be filling in one place with a 0. So my answer for question number 3 is 12850. Putting a comma there, so that would be 12,850. And again, if you wanted to put the decimal point at the end for these larger numbers, you can, but it's really not necessary. It is necessary in the tiny decimals, though. All right, let's look at question number 4. You have 2.75, and that's times 10 to the negative third. So again, we're going to be going to the left this time. 1, 2, 3 places. And filling in 1, 2. So our answer for this one is decimal point 0.00275 for standard form for question number 4. Okay. For the next part, we might need to determine then using possibly standard form, or if we can notice a pattern, how we would be able to determine what would be the largest or maybe the smallest number out of these numbers that are written in scientific notation. So out of these stars, which one has the highest or the lowest surface temperature? Well, I could actually multiply out every single one of these to determine which one has the highest and the lowest surface temperatures, and you can do that. So let's figure out what each one of these would be, and we can line them up with the decimal point. So if you looked right now, like 6.2 times 10 to the third, we have 3.8 times 10 to the fourth, and so on. But I also want you to notice your powers on 10 and see if you can also maybe start to come up with this answer in a different way. One thing you might notice after changing all these numbers into scientific notation, after realizing that we have the highest number with Bellatrix at 38,000, and I might say that's wrong, but I'm going to call it Betelgeuse, but Betelgeuse with the lowest surface temperature at 6,200. But there might have been a faster way of doing this. Since these are all powers on 10 and we all are in the tens position for our factor, you might have noticed that if you look at Betelgeuse, since it has only 10 to the third power, and if you look at this one here being 10 to the fourth power, this has the highest power at 10 to the fourth and the biggest factor at 3.8 in terms of comparisons to the other one at 10 to the fourth at the Sun and Rigel. So if you're comparing Bellatrix with the Sun and Rigel, the factors of 1.1 and 2.2, it's much larger. So we really didn't even need to multiply out these numbers in scientific notation. And if we're comparing the other star with the Betelgeuse star, yeah, they both have 10 to the third, but the factor of 6.2 is a little bit smaller than the 7.2. So these are other little shortcuts that you can look for and maybe save you some time instead of multiplying out all the numbers into scientific notation into standard form. So again, 6,200 for Betelgeuse, Bellatrix is 38,000, the Sun would have been 11,000, Aldebaran would be 7,200, and Rigel would be 22,000. The other part of today's lesson will be writing numbers in scientific notation. So to write numbers in scientific notation, you're basically taking what we just did and doing the flip-flop of it. So we need to come up with that factor that's in between 1 and 10, right, times 10, and then to some power. So again, if we are going to be writing a decimal, we're going to be going and writing a negative exponent. If we're going to be writing a large number, we're going to be writing a positive number, okay? And these would be the places that we'd be moving from the left. If we're moving to the right to make that factor, we're going to be making a negative exponent. So again, small numbers are going to have a negative exponent on 10, and large numbers will have a positive exponent on 10. So it's the reverse of what we just did. So if you look at this one for question number 1, the first is you have to remember your decimal point is at the end to start with. Okay, so we're thinking about moving that in between the 5 and the 0 at the beginning. Okay, so to now take that and move 1, 2, 3, 4 places to get there. So I'm going to take the 5 to make this a number between 1 and 10. If you wanted to put 0.0, you can, but you always want to make sure you have a factor that's between 1 and 10. Then write times 10. Count how many places you moved your decimal point. 1, 2, 3, 4. That's your power on 10. Since we're dealing with a larger number, it is positive. All right, let's try out next one. Let's try out number 2. So again, you want that factor to be a number between 1 and 10. So if you ripped off all the zeros and you put that decimal point in between the 2 3s, you would have 3.3 times 10. Now you're dealing with a negative exponent this time because you're dealing with a decimal. So now you have to count how many places you're moving that. So 1, 2, 3, 4, 5, 6, 7 places. So that would be 3.3 times 10 to the negative 7 power. Okay, let's look at question number 3, dealing with a large number. Again, you want the factor to be between the 2 and the 5 because, again, if you ripped off all the zeros, you would have a factor that's in between 1 and 10. So 2.5 times 10. All right, and again, 1, 2, 3, 4, 5, 6, positive 7 for our exponent. Okay, for question 4, we want the 5, but we actually want to include the 0 and the 6. The reason why we want to include the 0 that's in between the 5 and the 6 is because if I were to type this into my calculator, I want the same exact number to come back. So 5.06 times 10, I have a negative exponent this time because I'm dealing with a decimal. So 1, 2, 3, 4. So 5.06 times 10 to the negative 4 would be my exponent. For question number 5, again, to get that factor, you'd put it in between the first two numbers. So 6.83 times 10, and then that would be to the second power. For question 6, 4.5 times 10. We're dealing with the negative exponent. So 1, 2, 3, 4, 5, 6. Question 7, we'd be moving it to the very end because you want to make sure you have a factor between 1 and 10. And if you stopped in front, it would only be 0.5. So this is 5 times 10 to the negative 1, 2, 3. So 5 times 10 to the negative third. And then for question number 8, you want to make sure your decimal point's in between the 2 and the 4. So 2.45 times 10. You want a larger number, so we're dealing with a positive exponent because we're going to the left. So 1, 2, 3, 4, 5, 6. And again, you can use your calculator to double check some of these, but not all would work. And as a last step for today, in this word problem, we're going to have a couple word problems, but it says an album has sold 8,780,000 copies. How many more copies does it need to sell to receive the award? So the first thing that we need to do is notice that this album receives an award when it sells 10 million copies. So what we're going to do is we're going to take those two numbers and we're going to need to have to subtract those two. So let's take our calculator and let's do that. And it looks like we're coming up with, when we subtract the two of those, 1, 2, 2, and then I have 1, 2, 3, 4 zeros there. Okay, so again, I want to make sure I write this number in scientific notation. So again, I'm going to put that factor in between the 1 and the 2 and count 1, 2, 3, 4, 5, 6, and that will get me that answer. So the correct answer would be C. Okay, for this problem, the first thing I want you to do is I would like you to take a look and see at each one of these geological eras, not years, but it says eras. Okay, and I want you to order them from the earliest to the most recent. Okay, now when we talk about earliest, think about which one would occur the longest time ago. Okay, the most recent would be which one would occur, like, I want to say most recently, but you would have to think about like the closest in time span. Okay, your powers on 10 will help you to determine that. And you also think about, you can also use that trick I tried to show you earlier with that, because we have powers of 10 and they are all rounding in the hundredths position. If you want to actually multiply them out into standard form, you can, but you want to start looking at that and see if you can be a little bit quicker with this as well. So I'm going to pause the video and see if you can order this from the earliest to the most recent. So whether you needed to write them out in standard form or if you noticed a trick, the correct answer would have been Paleozoic, Mesozoic, and Cenozoic from earliest to most recent. So that would mean that the one that occurred the longest time ago would be the Paleozoic. If you look at the 10 to the eighths, that means that these ones would be occurring the longest times ago. So we'd be comparing the 5.42 with the 2.51, meaning that this one was, terms of longest or the largest number that we're dealing with, would be the Paleozoic. So that occurred the longest, followed by the Mesozoic. Then the Cenozoic only occurred 10 to the 7th years ago in terms of its base. Or if you look at the standard form, you can see that each one of these numbers would be occurring in terms of its order, in terms of how many years ago. So Paleozoic is the largest number, but we're talking about in terms of years ago. So in terms of the context of the problem, This would be the longest time ago, followed by the Mesozoic, followed by the Cenozoic. And the next problem, which is our last problem, I want you to try for questions 1, 2, and 3 to not convert them to standard form, but to rather look at the powers on 10 and see if that would help you to put the numbers in order from least to greatest. So, for example, if you notice, these are all ending in almost the same place value position. If you look, we can probably throw a 0 on here, and now we would be all ending in the hundreds place value position. Because of that, if you look, now we can actually use the powers on 10 to help us. Now we can put these in order from least to greatest. So the 10 to the 10th power would actually be the smallest power. So we would say 5.7 times 10 to the 10th would be the smallest, followed by 9.66 times 10 to the 11th, and then 5.76 times 10 to the 12th because of our powers on 10. If you look again at question number 2, we can almost use that trick again because we have, again, powers on 10. We're almost all in the same place value position, but we can throw on some zeros here. We have 9.90 times 10 to the negative 15th, 1.01 times 10 to the negative 14th, 7.60 times 10 to the negative 15th. We have two 10 times 10s to the negative 15ths. So what we're going to do is now look at those factors, because these would be the ones that would be our smallest. When we look at the 2, the 7.6 is a smaller factor. So therefore, 7.6 times 10 to the negative 15th would be smaller, followed by 9.9 times 10 to the negative 15th, and then the 1.01 times 10 to the negative 14th. Okay, in the next problem, we all have times 10 to the 8th. So now we'd have to be looking at the factors in front. So 1.2, 1.19, and 1.12. If I throw on that extra 0 in the factor, that might be helpful, because now we can see that 1.12 would be the smallest factor. So 1.12 times 10 to the 8th would be the smallest, followed by 1.19 times 10 to the 8th, followed by 1.2 times 10 to the 8th. And then finally on question number 4, we actually have a number in scientific notation followed by a percentage. We have some fractions, we have some decimals. The best thing to do when you have a number in a bunch of different forms is to make sure you convert everything into decimal form. So if you have 6.3%, remember that means per 100. So you should take your 6.3 and divide that by 100. So this would really be 0.063. 6.25 times 10 to the negative third, we know that means you're taking your decimal point and you're moving it 3 places to the left. You can actually take this one maybe in your calculator too, just to double check it. Let's see. Yep, this one did. So point, and I'm going to line up the decimal point on my notes and you'll see that too. 0.00625. Then we have 6 1/4, which I know is 6.25. And then we would have 0.625. Okay, so if I go back to my notes, I've got everything lined up by decimal point. So if I'm looking from smallest to largest, the smallest has to be one of the ones that has a 0 in the tenths place value position. So it's either going to be the 6.3% or the 6.25 times 10 to the negative third. To determine that, I'm going to move over to the hundredths place. In the hundredths place value position, I can see that there's a 0 and a 6. So the 0 would be with the 6.25 times 10 to the negative 3. So that would be that that one is our smallest. The next largest would have to be the 0.063, which would be the 6.3%. So we've done this one and this one. If I look at the tens place value position, the 0.625 would be the next. And the largest has to be the 6 and 1/4. So again, if you get those numbers all in the same place value position or the same form, meaning a decimal form, and then compare by looking at the decimals all nice and lined up, then you'll be able to determine the correct order. So again, this lesson was a lot. We had a lot of writing and reading numbers in scientific notation, ordering numbers with scientific notation, and some word problems. But again, a number in scientific notation is a number, it's a factor between 1 and 10 with some power of 10 with an exponent. If you have a positive exponent, we're dealing with a large number. If you have a negative exponent, you're dealing with a really, really tiny decimal.